Good morning, everyone. So it's a pleasure to introduce the speaker of our next session, Professor Yun Lee. Okay, good morning, everyone. It's a pleasure to introduce the speaker of next session, Professor Yun Lee. She has received her PhD from Xiang Jiatong University, China, and she held a position as AIST Fellow and STA Fellow at National Institute of Advanced Industrial Science and Technology, Japan. Later, she joined the Research School of Chemistry at the Australian National University in 2001 as a postdoctoral fellow and later was promoted as a professor in 2015. Her areas of research includes investigation of structure-property relationship of polar functional materials, novel catalysts, design and development for hydrogen generation and storage, and wastewater treatment. She has filed over 40 patents and published over 250 journal publications. Professor Yun has received numerous innovative awards and prestigious fellowship such as AIST and STA Fellow in Japan, ARC Queen Elizabeth II Fellowship, and Future Fellow in Australia, as well as she is also a Fellow of Australian Institute of Physics, Chair of Materials Chemistry Division of Australian Royal Chemistry Institute, and President of Australian Neutron Beam User Group. With these few words of introduction, I welcome you, ma'am. The session is over to you. Thank you.
Thanks, Dr. Sveti, for your very kind words for the introduction. So I'll share screen now. This one. So I have no idea which one it is. So please let me know if it's okay. No. It's okay now?
Yeah, we can see your slides.
Okay. First of all, I would like to thank Professor Namala Grace for the invitation and to give me the chance to talking about my research. And secondly, I would like to say a happy holidays for all the female researchers and female students, because today is the International Women's Day, right? Okay, so my topic, I change a little bit of topic because I think the strategy I'm going to present not only suitable for the photo-excited, the functional materials, but also for the materials in general. So I just changed that. Okay, we have been, it's a tough year, and so can you see my screen properly?
Yes. We can see your screen.
Okay.
We are still seeing the title page.
Really? So now it's better?
No, not yet. If you are using keyboard, you can just press this arrow.
Okay. Oh. Can you see now?
Not yet, actually. Still, we are just seeing the first page.
Yeah, this is the first page. This is still first page. I would just like to say if this one is okay? Or do I need to swipe the present view? It's a slideshow now?
Now it is in presentation view only. But if you want to change the next slide, then we will. Still, we are seeing the title page of your PPT.
Oops. I think that now it's okay. Can you see now? See this now?
Yeah. Now
Okay.
it's
Okay. Oh, so
now it looks okay.
look okay now. Okay.
Yeah, it's fine.
Okay, so we have been suffer a lot the last few years, last 1 year because of coronavirus, and in Australia actually is we also have another natural disaster, bushfire. So actually that's because cause a lot of the damages and damages and not only environment but also the societies. So they definitely we need to nowadays try to consider how do we deal with this kind of the consequence. They so the consequence of the climate change. So something in my mouse. I don't know where's my mouse. Sorry, something a little bit breathing. Can you see that? The mouse?
Yeah. We can see your mouse.
Okay, so it's definitely we need to think about how do we deal with this kind of the consequence of the climate change. So we need a moving from like for example, one important thing we need a moving the energy source from the dirty source in like we're using such as cows or other natural gas in the past. And so we're looking for the renewable energies, and then and also we need to have a very clean green energies and to fully decarbonization, has fully decarbonization. To do that, actually we really need to look at the key issues. How do we develop the energy materials? We need the energy materials which can satisfy all these requirements in the future for the practical applications, such as the catalysts for photocatalysis, for photoelectrochemical catalysis, electrolysis, to splitting the water to generate hydrogens, and such as photovoltaic the materials, and to transfer convert the solar energy to the electricity. So all this actually is come to the foundational point. How do we develop the good energy materials with with optimal performance? Which if we look back, the materials developed for the traditional materials and individually, they always have like prongs, cones, and they have strings on one side, and but a weakness on the other side. So it's very difficult for the one materials to be modified to achieve the optimal performance. So at least something here. So nowadays we can have a different way to do that. But today I will focus on how can we focus on the materials design, try to design the materials with even better property and performance. So in that case, we need some strategy or methodologies to design the new non-traditional materials that can overcome the limitation of the traditional materials and that enable to combine the two conflict strengths functions together. Okay, so that's actually is still fundamental materials science research, but we consider differently and try to find some way to develop some new functional materials. Okay. So I think most of the people working on the materials area will know that doping and substitution is the general tools for materials modifications. It actually starts from okay, from 1940s, 1960s, and actually you introduce separators, donors into silicon, and that's actually make revolutionary technology progress on electronic technology. That's to develop integrated circuits based on the N-type, P-type semiconductors, so that give you electrons, holes. But they bear in mind this one. This actually is based on the covalent compounds. Okay, so all the chemical bonding are covalence bound in nature. So in that case, they are extrinsic elements we introduced are pretty much they have a similar size and similar electricity. So that's in the past. This is strategy has been using since then, and especially after 1970s, and to modify all different types of materials. However, it get a lot of the confusing about what's happening in ionic compounds, because this not unlike the fully covalent chemical bonded materials, and they have they are ionic of chemical bonding, and they have different directions, and they can modify more flexible to change within a certain structures. So here I give the examples, for example, if we're using the X-ray part diffraction to determine the structure of the materials, which is in pretty much is the average structure in micrometer. That means your individual atoms maybe never in that lattice size. Okay, so that's based on the average structure. For example, with lithium, neodymium, titanium, which is one type of lithium battery materials, and their structure is a simple cubic phase with the titanium centered octahedral and oxygen corner shape to form the framework. And then in their edge, this frame edge cage, and actually you have lithium and neodymium occupied in one lattice size and randomly. That's like the picture you got from average structure. But reality is not, because you think about it, you can imagine if you have all the framework consists of titanium centered octahedral. So in that case, there are chemical environment for each cage are pretty similar. However, lithium, neodymium, they are significantly different in size, in valence, and in electronactivity. So in that case, if they put there to form the ionic compound, and their chemical bonding, valence, and charge distribution, all these things have to change. So that's actually this is the picture of the lithium neodymium titanate. You can, in a small scale, you see it's a 20 nanometer scale, and this is around 200 nanometer. The scale, you can see the different structure. So locally, they have a nanoscale interaction. So give you different local chemical region, local structure ranges. We have been working on these materials for 5 years. We identified over 280 different kind of the local structures. So this is the health, the materials from health. Okay, so in that case, and how do we deal with to identify where is the lithium? If none of the local structure dominated in these materials, how can we build a real precise relationship between structure and properties? And if you, in this scenario, if you introduce extrinsic ions to doping to modify the materials, what's the property you can get? If you doping ions located in different regions, of course, they will have a different property. So that's actually is tell us the doping substitution in the solid materials is structurally, chemically very complicated. Okay. So on the one side, we need to different tool to do more calculation to precisely build this kind of relationship. On the other hand, we maybe question us, how can we using this complexity for materials design? If this materials property came from the different the local structure, it's possible we can do something to create this kind of local structure to get a new property. Okay, so that's because if you the reason for this case, the lithium and neodymium, they are chemically are different. I can give you one example, and it's much simple. If you look at the lithium, you introduce the lithium barium titanate, and what's happened? So this is barium titanate is a typical ferroelectric material. So you got a beautiful ferroelectric hysteresis loop from the barium titanate ceramic sample. If we doping, the nominal composition is lithium 7% in these materials. You can write a chemical formula in this way, but doesn't mean it is a real case. So where the lithium will go? So if we do a lot of XRD and the neutron scattering, because lithium is a light element, so XRD doesn't give you the information intensity, structure information. We also do the NMR and ESR electron spin resonance spectrum, and so we found actually in this case, actually lithium is near 70% actually located in the glassy phase. Okay, so they are located in the grain boundary of the ceramics and in the amorphous phase they form. Rest 30%, and it's not exactly like you have a lithium in replace the titanium, and you introduce the oxygen vacancy correspondingly. What happened we found actually is if you have one titanium take or like empty, and the surrounding you have a 4 lithium to occupy this space. Within this 4 lithium, you have 2 are ordered, make contribution to this kind of the sharp peak. And also you also have a 2 lithium actually is dynamically disordered, more closer to the barium and in the structure, and also and contribute to this disorder peak, broad disorder peak. Another possibility is the lithium actually will induce the titanium reduction from 4 plus to 3 plus, and also form the cluster with 1 oxygen vacancy, 1 barium vacancy. So that's correct. Actually, because lithium is chemically unhappy in this barium titanate, so locally they will change the chemical environment. Okay. So and as a result, you say unlike the pure barium titanate, all titanium move one direction to give you a ferroelectric property. You have opposite the ions titanium will ion displacement. So that give you an anti-ferroelectric type, the physical property. Okay. So from that we can say we can actually divide the doping ions into 2 types. One is easy to dope the ions. So in that case, they are similar in size, similar in electron negativities. So you introduce them into the materials. It doesn't have a big impact in surrounding the chemical environment. They maybe have a little bit of moving around, but it doesn't change it much. So in that case, they just occupy that, replace the atoms, and to form the point defects or make the solid solution. So in that case, this extrinsic ion doping or ion substitution does change the property, but you will never create a new function. Okay, so they have a quantitative change, but not they have quantitative change, but not qualitative change. On the other hand, that's our new strategy. We try to introduce some extrinsic, we call the difficult to doping ions, such as lithium in the barium titanate. So they are quite different in comparison the ions in the host materials. So in that case, we can either using another atoms to create the synergic incorporation. So in that case, these two atoms, two extrinsic ions, they will correlate with each other to form a very unique defect cluster. That will give you a different, they create a different opportunity. All these difficult to dop ions alone cannot stay. They have to push the surrounding chemical environment change quite significantly to stay in this structure. Okay, so then these two ways. So in that case, we can introduce the difficult to dop ions. So this is not unlike the normally what we do when we try to modify the materials. Though it's very often we choose some items which are similar in size, and then they have a very close to each other in the periodical table, and then they can have a similar electronegativity. But here we deliver including at least one difficult to dop ions to significantly change the chemical environment. So that then as a result, we can form sort of the synergic incorporation to make the materials completely different. Okay, so we take the titanium dioxide as an example. So titanium dioxide generally have two structure at room temperature, rutile or anodized structure. Both have a linear dielectric materials with permittivity around 100, 200. Their band gap is around 3 EVs. So if we choose the titanium dioxide as a photocatalyst, they pretty much only sensitive to UV light. Okay. So in that case, it's a lot of work people has done, like introduce niobium into titanium. So in that case, you can introduce the electrons. So that is you can dop in as much as you want, and so this is easy doping ions. And then indium generally is difficult to dope because it's too big in size and the electron activity are quite different in comparison with the titanium. So normally, if pure only indium, you only doping into the materials a little bit, maybe less than 1%, or maybe even lower. So like 0.1%. However, if we have a niobium here, we can synergically interact together. Actually, we can form the defect clusters. So as you can see here, if these two extrinsic ions can integrate together, in that case you can create the defect complex, which not only have electrons but also have vacancies, and also this defect cluster is very big. It's related to 7-8 octahedrons. Okay. So based on that, and we found actually if we using indium niobium to create an environment to take the indium in that case to form the cold doping, so the electrons is localized. If you have only niobium doping into titanium, is the electrons is reduce the electrons from the titanium reduction actually is localized. So in that case, in this cold doping area, this case, we have electrons is trapped within these big defect clusters. So like that. So that's actually these electrons can moving around within this like a 7, 8 the octahedral range, roughly about 5 angstroms. So in that case, electrons are pinned, localized in this range. So like a free electrons, so they can hoping. So within these tracks, as a result, and we can get we can significantly increase the dielectric constant that's over 10,000. That's pure one only 100, 200. So in this case, at a low temperature, electrons are freezing. And if you have a little bit of energy to excite these electrons, and the electrons will be freely moving within this defect cluster tracks. Okay, so in that case, because electron is light in weight, so in that case, they can move in very fast. So in measure the frequency range, we can say it's no frequency dependence, no temperature dependence, until they have enough energies to excite these trapped electrons outside of this trap. Okay, outside, so in that case, the electrons become free electrons, so like a behavior like a metals, and so both the dielectric constant and the loss goes up. Okay, so that's actually you can find this kind of by introduce the difficult doping ions using another extrinsic ions, create the environment to take this indium in. So in that case, we can form the bonded correlated defect cluster to significantly change the property. Okay. You may think, oh, this is, well, yes, I see the results, but how this may happen? Okay, how do you introduce the physically practically introduce these difficult to doping ions into the materials? And here I'm using the wide chemical synthesis and hydrothermal reaction, and to see how can we introduce the indium niobium into the anodize the nanoparticles, and that will show very clear picture how this how difficult to doping ions are introduced into materials and interacting. So this is a so this is if we this is niobium. If we put a certain niobium concentration, and the niobium can be, you can see from here the reacting time, niobium can immediately reach your expected doping levels. Okay, so if you want to 5% of the niobium, in that case you just put 5% of the niobium, you got it. Okay, so this is easy doping ions. For the indium, if you have you want to 5%, if you put 5% actually in the solution, but then you never get it, no matter how long time. And you need a much higher concentration of solution, then you can, with a certain time, and they will reach an equilibrium state, and gradually this indium concentration level will go to the 0.5, and you're expected to the solution called doping solution. So in that case, so it just take a very long time. So that's because this is difficult to dope ions. If this ion indium only alone, and you cannot reach the 5% whenever, no matter how long time of your reaction time. Okay, so that's the you can see the clear picture actually. So you do have using niobium during the reaction come to the structure first, and then they create the environment and attract more indium to reach the equilibrium state. So this is most important if you're going to synthesize, we need to reach the equilibrium state. Okay, so as a result, because you got the niobium to have indium to take indium into the materials, so in that case, the indium the doping level can be much higher. So in this case, we can doping indium up to 15%, and in the meantime, niobium 15%. That means totally you have 30% of the doping in titanium dioxide. Okay. So that's the examples. How can we introduce the difficult the ions, difficult to dock ions into materials to form the correlated defect clusters to change the property. So that's is this kind of the defect formation is very complicated. So this one, like for example, if we change the titanium, titanium, so in that case, they got a different structure, and you also have a vacancy as well. And then if using magnesium is the Indian, and then you have this kind of structures. So in other cases, we always have a difficult to dock the ions. Okay. But the complexity of this kind of this strategy and is also present here. Like for example, using aluminium, and it's like too small. So in that case, you actually aluminium, unlike the Indian, aluminium will partially go to the interstitial position, and in that case, and they never you never observed any oxygen vacancy in these materials. Okay. So that's the complexity of this co-doping with at least one difficult to doping ions. Okay. Such kind of the difficult to doping ions also doesn't have to be doesn't have to have a second extrinsic ions to create the environment and to accommodate them. And you can also like a push forward of the local structure environment, even like a push, like for example, oxygen away, and you can actually, so this kind of the difficult to dop the ions will form the defect class with the oxygen vacancy. Okay, so this kind of because magnesium is the difficult to doping ions, so these permanent dipoles will significantly affect the surrounding chemical environment. As you can see here, so this is a simulation result indicated that the ion surrounding titanium were moving off the center from the lattice sides. So as you can see, even this kind of this titanium away from magnesium, a few angstrom still be affected. So that locally, even is affect actually locally they change the structure, so make this titanium dioxide lose the central symmetry. As a result, you can observe sort of the ferroelectric behavior. Okay. So we can, so in this kind of materials, so as a result, so if we're doping 0.25% of atom, it's a very small amount. Because this difficult to doping ions significantly has a significantly affect the surrounding chemical environment. So locally, your variation like actually is quite large, maybe increase like from 0.25, maybe from like 5% or 10%. So in real case, so in that case, the impact is very big. So you can observe this kind of the polarization hysteresis loop like ferroelectric. Of course, it's not a ferro. Okay. So that's the difficult to doping the ions can be accommodated by extrinsic ions you deliberately to introduce. So they are correlated to each other to form a defect cluster. Or you can significantly locally like broken this structure to create the new defect cluster regions, and as a result affect the property. Okay, so that's actually is the one strategies. And to how now I want to say give an example to show you how this strategy will affect the photocatalyst. So we know the pure titanium dioxide has a like band gap around 3 EV. So in that case, this is only sensitive to UV light. It's a lot of work to want to take this titanium dioxide working in the visible light range. Okay, so but unfortunately, it's not very successful. It's one of the things to move into visible light is, well, for example, typically you're using nitrogen to replace oxygen to increase the valence band. So in that case, you can narrow band gap. But it's nitrogen because in comparison with oxygen, they're quite different. So it's no way it's only like you are assuming, oh, nitrogen is 3 minus. So in that case, I will using 2 nitrogen replace 3 oxygen sites and to generate 1 oxygen vacancy. So it's not that, because the electronegativity different, that will be make this defect cluster more complicated. So in that case, the nitrogen, if you have a nitrogen around, so you not only generate the oxygen vacancy, but also reduce the nearby titanium-3. These two cases located in the where the nitrogen are in different locations in the titanium dioxide. So either case, they were slightly improved light absorption and slightly increase the absorption in the visible light range, but not much. The reason is this kind of the oxygen vacancy of titanium-3 is not provide the ideal environment so you can attract more nitrogen. So the nitrogen contribution level is very low. So we tried different way, and actually you only can go to 3% of the nitrogen introduced in this case. So now, because the nitrogen is difficult, so now I'm thinking if we can create another chemical environment to accommodate more nitrogen. So, and also in this case, because the titanium-3 reduced, you got the free electrons as well, and also oxygen vacancy, they are not very tightly bonded, and in that case, you will have a recombination. On the one side, you reduce the band gap and you generate more electrons, but on the other hand, you maybe create the recombination center. So based on that, we using our new strategy try to pair the niobium and the nitrogens. So in that case, the niobium nitrogen, they always try to neighbor each other, not far away. You can a little bit far away from each other, but not too far away. So in that case, this niobium nitrogen bonding, niobium nitrogen 1-to-1, and so in that case, not only reduce the band gap, but also avoid to generate a recombination center. So you can see here, and also this kind of the environment so allow you to attract more nitrogens, so that give you much stronger visible light absorption. As a result, so you can see here, we have that's a comparison with the 3 sample, and one is the niobium have a concentration higher than niobium, and another is the nitrogen equivalent to niobium, another is the nitrogen actually less than niobium. So we call the nitrogen rich, nitrogen equal, nitrogen poor. As you can see, only the niobium and the nitrogen to form the pair, then they give you a much better absorption and a much better photocatalysis effects. Okay, so that is how can we using this defect strategy to modify the materials to modify the photocatalysis. Okay, so similar strategy we can using for other materials design as well. Okay, so that is one new strategy. Another strategy is come to the idea come from local and average structure and property. Before I mention we go to the photo-excited function materials, I will give you these examples and to show you how this local structure actually affect the property. So this is bismuth sodium titanate, barium titanate, and it's a typical lead-free piezoelectric materials. And so in this morphotropic boundary, so and here, and generally this so this phase transition from ferroelectric rhomohedral to ferroelectric tetrahedral. Okay, in this so-called morphotropic phase boundary, and we can get the optimal piezoelectric performance. Okay, so there's a lot of people working on that and try to understand why this excellent piezoelectric performance property only observed in this phase boundary region. It's in the past, they say, oh, that's a phase boundary. In that case, you must have a two-phase mixture. But if you physically to make mixture this two-phase, they will never get this property. And some people, and that's the so it's not just a simply two-phase mixture. Another the previous research, think this is when they try to using X-ray power diffraction, try to identify the average structure, they found this is monoclinic. And but from crystal chemistry point of view, you can, if you consistently change the chemical composition, you cannot have a low symmetry crystal structure in between two high symmetry crystal structure. This doesn't make sense. So what happened here, actually, we do the systematic the electron diffraction. If you can see actually a part of the strong spot, which is reflect black diffraction, and you will see the streaking line as well. What happened here, actually, these strong dots, and you see this is 01, this is 310, this is 311. So that actually half of 311 actually is a satellite diffraction. That tell you the octahedral rotated around 111 in around 111 actually is has this kind of the ordering. If we're using the green indicated the octahedral rotation this way, and then green is rotated the opposite way. So you have a if we have a green, this kind of the octahedral tilting ordering. But however, if we find actually you have a little bit of spots here as a half 110, actually is because this rotation you have a stacking force. Actually, this rotation is stopped. So gray, you got a gray, and a green, green. So here is like a mirror, got a twinning of the stacking force of the octahedral tilt. So in that case, this area corresponds to high resolution image of structure. You got a few nanometer the correlation length area. Okay, so that's actually we found is in these materials you have a within under the umbrella of the average structure, you have the local structure that came from the octahedral tilting. Okay, within increase the concentration in that range, and you will find that this half 111, this half 111 satellite diffraction become weaker. This half 110 becomes stronger. So that's indicated in this kind of the stacking force generated, induced the local structure gradually grew in length, in size, and in correlation length. So that actually until you see the diffusion scattering, this is straight line. That's these atoms moving along the one direction. The ion displacement like bismuth, sodium, titanium. But if you see the diffusion cycle here are different in comparison to this one, this actual diffusion indicated the long-range ordered 111 direction in the rotor-hydrogen structure has completely broken, and they switch to tetrahydro. So what happened here in this boundary is within the boundaries, no average structure change. Instead, it's the local intergroup structure gradually change in size, in correlation length, generated, make a contribution to optimal performance of the piezoelectric property. Okay, until at a certain point, and this structure completely damaged. Okay, so that's it's a very interesting the fact in the phase transition area, you don't have gradual phase transition. Okay. What happened is your local structure gradually change. Okay, so based on this strategy, and then we want to using like to local structure, local chemical regions, by introducing this local chemical and local structure range and the environment, we try to create new materials, try to link the two different functions together. Okay, so this actually is some people in like Lee and they published a paper in Science. In 2015, actually is very indicated very clearly. So this is kind of a strategy, but they haven't really systematically developed that. So in their case, actually strontium titanate and matrix, you have a polar NanoRegion. Strontium titanate is not the ferroelectric, but you have a polar NanoRegions in these materials. If your strontium titanate in dimension is much larger than the polar NanoRegions, you wouldn't see the ferroelectric property. But because the strontium titanate itself is not ferroelectric. But if you reduce the thickness of this thin film down to the similar comparable the thickness with the polar NanoRegion dimension, so in that case, your polarization will go up. This is a curve you can see here. If your thickness of thin film at 60, you don't have a polarization, but gradually reduce the thickness, and you will see this polarization. Okay, so based on this strategy, and we actually have recently done a certain work, try to nanostructure the materials, try to enhance the photovoltaic materials, enhance the photovoltaic the properties. So you may say maybe later on this afternoon you will see a lot of work done on the hybrid ProSky. Okay, so what I want to do here is, so this generally semiconductor photovoltaic is used narrowband semiconductor to form the junction and to give you a photovoltaic effects. So you can excite the electrons, and then this the photo current is quite large because of narrowband gap, but the photo voltage is very low because they're limited by the junction or barrier height. But on the other hand, the bulk function photovoltaic effect occurred in ferroelectric but never be used. They can generate the photo voltage over near thousands, but the current is, because the ferroelectric is the insulating material, electronic insulating materials, and the photo current is very low. They never be useful as photovoltaic materials in practical application. So what I want to do is try to combine this, try to make the semiconductor materials to not only have a large current, also have a large voltage. So that's overcome the barrier height of the junction. Okay. So So that's actually is a fundamental the purpose to do that. Okay. So for that, for example, we choose the bismuth vanadium oxide, and so this generally this is non-ferroelectric materials with a band gap of 2.4 eV, and they have a you can chemically introduce the local chemical NanoRegion, which is Bi4V2O11. So in that case, it is ferroelectric. So these two materials you can switch by control the synthesis condition. So as a result, you can reduce the thickness for the similar height of the similar in comparison with the polar NanoRegion. So in that case, you can build the very good nanostructure materials, and so that enhance the photovoltaic effects. So you can see here from the image, so that's the height of the less than 20 nanometer, and you got some regions as a local chemical region. And you can see here, if the thickness of the thin film is 30 nanometer, you don't have a good ferroelectric property. If you have 10 nanometer, and your property is much good, much better. And if you look at this is a ferroelectric polar domain, if you apply the different voltage in different direction, you can see the domain contrast from this domain image. But if you increase the thickness, you couldn't see that. Okay, and then we can deposit on a transparent ITO thin film transparent electrode on top of this. So only 10 nanometers thin film with 2 electrodes, and actually we create a heterojunction in this narrow band gap. In the meantime, we generate a ferroelectric that can build the internal field, separated the photoexcited charge. So in that case, we can increase the photovoltage up to 2.4 volt, and then current will be 300 microamp per centimeter squares. So that gives you near 2% of the power conversion efficiencies. You may say by comparison, the hybrid ProSky or silicon-based PV materials is still not much so high, but the most critical point is the voltage is over that limitation of the junction. Okay. Similar things we also do for the bismuth niobium oxide. So in that case, we can introduce a defect, and then we make these materials has become ferro and non-ferrous, and we pack them together and to form interface junction. Okay. So and as a result, again, we can form, actually here is a home junctions, and then we can enhance the bulk photovoltaic effects. Okay, so that's the few examples indicated how can we change the local structure environment to make materials unique, which can combine different weaknesses together and to different strengths together, and to remove the weakness of one of them, and then to make materials more useful. Okay, of course, this is just a very beginning of the work, but only 10 nanometer thickness metal oxide. You put the 2 electrodes to get this 1-2% of the power conversion efficiency, and it is quite good. If we optimize that, we can get even higher, like optimize device structures. The most important, because this kind of materials are very stable. We can use in high speed, like high temperature, like for space technology, or different extreme condition environment. Okay, so that's from these examples, and we can say introduce the difficult to doping ions, enable to create new functions, introduce local chemical structure environment to generate a new interaction, and we can create the new functions that overcome the weakness of existing traditional materials. Well, the more challenging work is very complicated. We do some computations, some bound balance, some calculation, DFTs, and in the future, we need to combine the machine learning and try to develop the platform to make this methodology more useful. And the second challenging thing is we need to extend the current defect chemistry. That hasn't, most of the traditional point, the defect chemistry in solid is point defects that will modify the, as I mentioned in the beginning, will modify the properties, but not significantly change the property. We need to develop this, extend this defect chemistry. We also need to extend the crystallography that it has been existing for 100 years, but that's we can using that traditional crystallography describe the average structure properly, but that doesn't cover the local structure, local chemistry. How can we develop a new crystallography platform and to cover that? That's actually is critical for future the nanomaterials designs and you in different lenses to consider different scale, the real structure, real chemistry. Okay, so finally, the most challenging is how can we develop methodology to control, realize that in practical way, and then so we can assemble them and to make a new functionality. Okay, so that's the challenging work. Finally, I would like to thank my group students and postdocs for their continued contribution to this research area. I've have a lot of the collaborations from other universities, but I would like to really appreciate my long-term collaboration with computational chemistry guy, Dr. Teaching physics for the computational physics. And also I would like to thank all this funding support from government and industry. Thank you.
Thank you, ma'am. Thank you for such an interesting talk. Now we have some questions from the participants. One of the questions from Mr. Jobin is asking that on the basis of molecular weight of the dopant, which is the best method out of solid state synthesis and wet chemical method?
I think this the both are fine, but we need to carefully control the precise condition to reach the equilibrium state.
Okay, thank you. There's one more question from the same participant, that how does doping affects the large scale or bulk scale production of the materials?
So for example, the colossal permittivity one, that's a good examples. So for the dielectric materials, generally, if you increase the dielectric permittivities, and you will increase the dielectric loss. Okay, so in this is to conflict the parameters. It's very difficult to get a balance right. So that's why the people have been trying to develop the colossal permittivity materials for over 2 decades, but have never been successful. So the example I show you in my talk is vacuum materials. So in that case, so if you reach the equilibrium states, and so this defect can form, so will give you like a significant property change in bulk for the bulk material.
Thank you, ma'am. There's one more question from Dr. Jin Min. Is asking about what kind of band gap is more suitable for photovoltaic solar cells in terms of the band gap.
So that's the question. I think it depends. If it's a semiconductor type one, so generally you can go down like a one, around the 1 or 1.1, 1.2 above. So that's the semiconductor PV materials. For the bulk photovoltaic materials, traditional is very high. We normally is over three, up to 3.8 or something, occasionally up 4 EV. So, but that's why actually for ferroelectric bulk PV effect has never been practically useful. Okay, so we can reduce, in that case we can, so through this local structure design, actually we do, because traditional ferroelectric, if you reduce the band gap and you actually degenerate the ferroelectric polarization. So in that case, the internal field cannot be built properly. So that's why it's difficult if you focus on the traditional materials, difficult to make the good the PV effects. But from this kind of the new strategy design, we can actually, as I show you the two examples, you can choose like a narrow band gap materials, and you can generate the ferroelectric like the behavior to build the internal field. So they can synergically collaborate together, couple together. So in that case, you can excite the electrons and you can separate it. So that's why you got double win. You can increase the photocurrent. In the meantime, you can also to increase the photo voltage. For the band gap, I think we currently we go down to 1.8, 1.7. We haven't tried further lower, but in principle, you can go even lower.
Thank you, ma'am. Thank you for answering. So, and thanks for such an interesting lecture, ma'am. Thank you.
Thank you. Thanks, everybody.
So on behalf of the organizing committee, I would like to thank Professor Yun Liu. So the next talk will be given by Dr. Aida, starting from 12:45. So I would like to request all the participants to join with the same link at 12:45.
You submitted one, Swati. You said, you got that.